Okay, thank you. Okay. Hello, everyone. First of all, thank you so much for giving me this opportunity to share our research work. So the paper which I am going to present is a cross-domain threat screening and localization framework using vision transformer and self-supervised learning. I am Mohammad Usman Akram, and this work is being done by one of my PhD student, Amara Naseem, and we are from National University of Science and Technology, Pakistan. So coming towards the introduction, on daily basis, million of travelers they use airports, and the airports are generally one of the highly secure areas, and they are also vulnerable to different security threats. So although the airports are continuously under surveillance through vision like cameras, or they use X-ray scanners to scan the baggage, but still that is very subjective, and the technology on daily basis keep on advancing to improve to see the concealed threat items which are placed within a certain baggage. So that is one of the possible computer vision application where the people are working. And as per some of the reports in Texas, they like find record number of guns with different people who are using airports. So it means that we certainly need sportive systems along with the men security persons who are placed in the airports. So coming towards the related work, the people in computer vision, they are working in this area, and they are analyzing the this baggage videos, X-ray videos using 2D and three-dimensional convolutional neural networks, or the deep learning based methodology, and or even the conventional image processing based methods. So what we have shortlisted, that we have divided this problem into two phases. One is the pre-screening phase, where you have to screen the all the videos or the ongoing certain videos, whether it contains any threat items or not. And once that our flag is raised, then you can further dig into the problem and see what that particular item is. So the people, again, the people are researchers are using convolutional neural networks, transformer based networks to do the initial pre-screening, and for the further detection, along with the detectors like YOLO or other kind of scenarios, one of the problem is the lack of supervised data or the lack of labeled data. So self-supervised methods are also in place for this particular problem. So what we are trying to do here is, like at very abstract level, we have two modules. One is the initial pre-screening module, so that we should not be focusing on each and every frame. We should tag a particular frame which may consist a threat item, and then if the tag is raised, then we will go towards the self-supervised object detection module. So these are a little bit more detailed presentation of the same methodology, where we have different modules. First, we do the threat pre-screening. Then we use the super picture generation, which I am going to discuss later. And based on that, we do the training. And at the real-time testing, we have included one of the things, like where we worked on the best suitable spot image selection for one-shot learning and one-shot testing at the real time. So in the pre-screening, we utilized the customized vision transformer, which is trained on publicly available datasets, and that the datasets, they are gathered in a way that generally we have the it's kind of an anomaly problem, where we randomly appear a threat item. So the data sets, they are curated in a way like out of 1,000 or 10,000, let's say, scans, there would be one anomalous scan where which would be a threatening one. So considering the imbalance of the data, we tweak with this vision transformer, and we come up, we trained it in a way that it detects the threat items at the very first stage. Then going towards the self-supervised thread localization. The first one is the super pixel generation, where we use graph-based super pixel generation module, which groups together the pixels to separate them from the background and generate the pseudo labels to cater the problem of not having the labels with us. The next module which we added here is it's adaptive local prototype pooling module, which is again a deep learning based network which takes the features from the query image, this spot image, and generate the augmented version of that spot image in form of query and see the similarity between the features of the spot and the query one. And once the local similarities are computed, those are grouped together to have a global similarity using softmax to finally have the final generate the final result in terms of training, so that based on the pseudo labels generated from some of the uh, few collected spot images, the model is trained to generate the outputs. So during the online training, we combined regularization loss and the cross entropy loss to have a generalized kind of learning, so that from few query images, the ALP net it get trained on to generate the final outcomes in terms of where a particular thread items is. And one of the module which really affect the whole processing is the selection of spot image. So out of all possible pool of spot images which we already have within our, with us in our database, so we select the best suitable spot image out of that whole pool. And here we utilize ResNet 101 to extract the features, and then cosine similarity is used to find out the best suitable spot image. And that spot image is used at real time along with the input text frame which was uh, like tagged as thread, frame having some thread. So that frame along with the spot image is again passed through that ALP net to extract the final to localize the final thread, whether there is any gun or knife or any shuriken is present in the in that particular frame. So in order to validate this whole scenario and to see the cross-domain adaptability, we have utilized multiple publicly available datasets. One is the Compass XP, another one is GD X-ray, and then we have also have 6-ray images. All these are baggage X-ray images which were collected to have different to identify different kind of threat items, and to and we also tweak the parameters of VIT. These are the performance evaluations which we used for the classification. We utilize F1 and accuracy scenarios, and for localization we use mean precision, IOU, and RMSE. So initially, the first one was the pre-screening, where we see whether a particular frame contain any threat item or not. So we do see the domain shift as well. Like we trained on one particular data set and we tested on the other one, and of course, on a total blind testing, the model was not working in a good way. Then we selected a subsample from that cross-domain dataset, and we combined it with the training data, and then we recheck it. And of course, the model were now trained in a better way, and they were detecting the threat with relatively higher reliability. Then we also compared the localization results with other state of the art. And for this localization, what we did that we trained it on one particular data set, and we of course we selected few images from that as initial uh, uh, initial frames, and then we generated the query images out of those, and we compute the IOU and MAP for these datasets. And we also did the ablation study in terms of whether we include the sport selection module, intelligent sport selection module, or how the method performs with the selection of sport module and how it performs without the selection of sport selection module. So again, there was a clear jump in the reliability of the whole model when we include the sports selection module, which again is based on ResNet 101. And once we select the best sports images to support the whole processing, that overall impact the accuracy of whole system. So here are few visualized results where we are detecting from one data set, and this is for the other one. And again, some of the randomly selected images where we are detecting guns, knives, and shurikens. Mainly for this particular research, we focus on knives and guns, whether they are present in that. So the environment gets changes within the data sets. Some are the very clear images where each item is very much clear and we can localize it with good accuracy, but some of the environments are very cluttered ones. So that is the scenario where the selection of a good spot image comes, and that plays the role. So as a concluding remarks, the thing which we see through the ablation study, that was like the this whole self supervised approach that depends on the selection of best selection of the spot image. So it depends how good you extract the spot image from a pool of available images, and then you utilize it to have self-supervised training. So with this, I thank you so much.
A very general one. I had a few of them. This was a problem that was no longer with us.
Yeah.
So is that the case, or do we still have?
No, we still have this problem with us in terms of cluttered and very concealed environment, because as we being researcher or the technologists, we are advancing, so as the people who want to do some malicious activity, they are also advancing. So we are doing this research in collaboration with PIFA University UAE. So where what we are trying to do is like we have our own X-ray machine with us, and we are trying to make more as challenging environment where we are placing even the toy guns, the 3D printed guns, or the those kind of threat items, which are not easily like detected from a scanner or can be easily passed through a human eye. So the research is actually going towards that, but in general, it's very much like solved as the.
Okay, thank you. So I've been told, and we have been given permission to have copy for 10 minutes.
Yeah.